Hi. Shall we go ahead and get started? Thank you. All right. I just put a little inspiration up for you while we were waiting. So that's the original paper. Okay. So let's go ahead and get started. So I have a couple of administrative things to say. So I heard from a couple people that there were some problems with the slides in the sense that the green wasn't really visible. Is that right? So fortunately, I only used the green for organizing things. So it just, if you didn't see the green, it just looks like I was disorganized. But there isn't a lot of green on the slide, so hopefully that'll be okay. Secondly, people said that the subscripts were really hard to read. Okay, so the slides have been posted on my website, so the one that Dan put the link to. Okay, bless you. There are also some on the OPLSS website, but the ones on my website are more recent. So Jim had to post the ones on the OPLSS website, but I don't want to have to, every time I look at them and think, oh, it would be a little bit better if I did this. I don't want to, sort of bombard him with new versions. So if you want the most recent ones, you can have a look on my website. And if you wanted to look there while I'm talking, have them up on your laptop while I'm talking, that might help with the subscript issue. Okay, so here we go. So remember that this is a course about parametric polymorphism for system F, or parametricity for system F. And that the goal is to extract the vibrational essence of parametricity and then use that to generalize Reynolds construction to more general models of parametricity. And there are 4 lectures, as you know, and today is going to be the introduction to vibrations. Okay, so after all, if I'm going to build a vibrational model of parametricity, then I should tell you what a vibration is. Now, I could just right now say, so vibration is blah, 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 blah. But I thought it would be nicer if I worked up to it a little bit. So the definition of a vibration won't come until somewhere toward the end of the lecture today. Okay, so I'm just going to sort of work into it. So where were we? So last time what we did was we recalled Reynolds' standard relational parametricity. And as I said, this is our main inspiration. So the idea on yesterday was not for you to understand all the details of the construction necessarily. I mean, if you did, that's good, or but if not, that's okay, because we're really using Reynolds construction to just as a source of inspiration. What we're going to do eventually is view Reynolds construction through the lens of what's called the relations bifibration on set, but you can't do that yet because we don't know what a fibration or a bifibration is, although you will hopefully at the end of the day. And then in the last lecture, we'll generalize. And then, of course, since we're generalizing, Reynolds construction should be an instance of that construction. So it should be such a model, well, if you ignore size issues. Okay. So to work up to the idea of a vibration, I want to look at indexing. So I want to look at index families of sets. So this is our motivation just for today. So a vibration is going to capture the idea of having a family of categories that's indexed over another category. So I'm going to have this family E, and the family is going to be indexed by the category B. So every time I have an element or an object, B in B, I'm going to have a little category for it. Okay? So a bifibration is a functor from this collection E, so from some collection E down to B. So typically you think of E as being the union of all these categories EB. Okay? We're going to call B the base. We're going to call E the total category. And then U is just a functor. And you know about functors. And like I said, intuitively, I think of E as being the union of all of these little EBs that I have. Okay? And this U has to have some properties that are useful for describing indexing, but I'm going to work up to those. That's the thing I'm going to work up to. And let me just remind you that we're interested in indexing because Reynolds construction was indexed by types, right? So every time we did something, we said, all right, well, what does it mean to interpret a type? What does it mean for two things to be related at a type? So everything was sort of done at a type. So that's this idea of indexing. Okay, so I'm going to come back later on and tell you about these additional properties. Okay, I haven't told you about them yet. And what I've got right now is just this functor with a total category and a base category. Okay, that's it. So to talk about indexing and to kind of work up to the idea of a vibration, let's look at a simple case. So let's look at the case where we're indexing for sets. So B, my base, is going to be a set of indices. I'm going to call it I for indices. And E is going to be, this E here, is also going to just be a collection of sets. So my base category is going to be a set, and my total category is going to be a set. It's going to be a union of a bunch of little sets, one for each element of B. And then U, my functor, is going to map X, the total category here, down to the base, which in this case is going to be I. So I for indices and X for the elements. That's the idea. And we're going to map every element at little x in X to the index of the set that it's a member of. Okay, so this is, right now, since I haven't told you about these extra properties, this U is one of Ed's sorting hats, right? Not the big one that sat on the houses, but the little one that sat on the people. The one that said, okay, you belong to this house, right? So if I have a person, a student, then my U is going to tell them which house they belong to, and the index I is the name of the house. Okay, that's the idea. So you call U a display map for this family. I'll use that terminology a little bit. And we tend to draw it vertically like this. So here I've got, these are all my people, these are the houses, and U is a map sending the people to the houses. Okay? But I told you before, it's going to be an extra magical sorting hat because it's going to have these extra properties I haven't told you about yet. Okay. Then if you look at the inverse image of, look at an element I, little I down here, and look at its inverse image under U. So what things go to it under U, right? So which people are in the house, right? Then you call that, we denote that by X sub I, if I is my element, and we say that that's the fiber over I. Okay? So the way I think of it is something like this. Try and draw this really big. So I've got my set I down here, and that's my base category, and I've got my total category up here, and I pick an element I, and I've got this like little balloon of stuff that maps to it under U. Does that make sense? So my world is populated by these little balloons. Okay. All right. So let's just take a moment and so we have these index families now, right? So I just want to show you some things that you already know that are instances of index families. So do you remember the slice category from Ed's, what lecture was that, 3 maybe? 3rd lecture. So remember this, you take an object, I in set, and you look at all the things that can map to that object I. So an object in set over I is a function from X to I, right? And a morphism in set over I, you already know, well, it has to go between two objects of set over I. So here's one, and here's another one, right? Here's one, and here's another one. And what's the morphism there? Well, it's just a map from the domains that makes this kind of diagram commute. This is exactly the definition he gave you. Okay? Hopefully that looks familiar. Okay, so what I want to point out is that you can look at this map G as like not just one function, but a little family of functions. Because you can say, well, what kind of family of functions would I have? I want to have one for every index, so one for every element of I here. What should it do? Well, it has to make this diagram commute. So it should take things over here that map down to I, so things of index I, you might say, to things over here that map to I. So I can imagine that this G is really a little family of maps G sub I, where each GI maps to things over here that map to I to the things over here that map to I. Or in other words, we map x prime sub I, that was our notation for the things that map to I, to x things in x sub I. That was our notation for the things over here that map to I. Okay? And identities in composition of the morphisms are, well, these G's are just morphisms in set, so their identities in composition are just inherited from set. Okay? So that's an instance of something that you know of. And this is all about indexing, and you can look at one morphism and you can see it as something about indexing. Okay, so let's generalize a little bit. We're going to generalize slowly. So do you remember the arrow category? That was, I think, another example. Okay, so here, okay, so let's go back. So here, the objects in the slice category are maps U from X to I, but the I is fixed, right? And that's the difference between the slice category and the arrow category. In the arrow category, the codomains can vary as well. Okay, so an object of set arrow is just a function U from X to I in set. And here I is just some index set, and those can vary. So it's not, my I is not fixed. So if I have a couple of objects in set arrow, here's one. I've got a U going from X to I, where I is one index set. And here's another one. I've got a U prime going from Y to J. Then remember that a morphism there is just a pair of arrows, G and F, that make this diagram commute. Okay, that's the little generalization that you get when you look at the arrow category. But just like before, we can actually see this G as a family of maps. So right now it just looks like a map. But I want to look at it as a family of maps. What family? Well, a family GJ. And what does a J do? Well, let's see. If I look at something here that maps to J by U prime, then I want G to map it to something over here that goes by U to F of J. So that's how I just take my morphisms and I can, my morphism up here, and I can kind of see it as something indexed. Okay, does that make sense? Okay. And again, identities in composition are just inherited component-wise from set, because every morphism in my little square is a set morphism. Okay, so a little bit more indexing. It was hidden. And I also want to say, because it's going to be useful, that set arrow induces what we call a codomain functor. And what does it do? It maps one of these objects to its codomain. So it maps U from X to I, just to I. And it maps the pair GF, if I have a morphism GF, from one object to another one. It just maps it to F. So basically what it does is it takes that square and it just squishes it down onto the bottom level, right? Okay, all right. So that's what we have. So I swear this is going to lead us to vibrations, but it's going to take a little bit. So I want to talk about substitution, and I want to talk about it in terms of things that look very, very much like the diagram on the last slide. So let's suppose that we have a display map, right? That's this U going from X to I. So my X is a union of Xi's, and I've got an index set I. So same setup as before. Substitution along a map F going from J to I is going to turn my index family Xi into a new index family Yi. And it's going to have the property that the things in the new family that map to J are the things in the old family that map to F of J. All right, so it's helpful to have a picture. So I'm just going to redraw the picture that's up on the slide on the board, but I think it'll be helpful to have it here for reference for the examples I'm going to do in a minute. So we draw the same picture. So I've got this object U going from X to I, and let me not start with this. So that's one thing I have. And the other thing I have is this map F going from J to I. So is that big enough that you guys can see it? Hopefully it is. Okay. Or is it really enormous? Okay. So what I want to do is make a new family that's over J. And the way I'm going to do that is I'm going to make something called the pullback. So I'll just call it Y right now because that's what I've called my family. So a pullback is an object together with two, well, they're called projections, so that this diagram commutes. So that's one property. Okay, and I should call them the same things. I called that one U prime and G. Okay. But the other property is that if I take another thing that has a map to here and a map to here, like Y did, then there's a unique map. So it's the least such thing. Okay? So that's this idea of I'm describing something by its universal property. And so I'm not going to prove that pullbacks are unique up to isomorphism or anything like that. I'm just going to say you can do that because you have this great training that you got from Ed's course, right? Okay, so the pullback, this Y, is going to give me my, my new family. And how is that going to happen? Well, if I look at the things in Y that map to some object in J, then because this so let me just get rid of this extra stuff for the moment. Then because F maps J to I can see that, and because this diagram commutes, I can see that Y is going to map, that U prime is going to map things in Y to J that are the same as what U maps down to F of J. Okay? So that's how I get a new family. So if you're in a category like set that has terminal objects, a pullback is just a product. That's why I called, I don't know what I've done with that. That's why I called these maps projections. I'm not going to write them using pies or anything right now because it's more helpful to have them written this way right now. But these maps are called projections. So the pullback is actually the object and the two projection maps. Okay. And we put a little corner there to say it's a pullback. But it's a product. And so what you can see is that what I've done is I've said Y is the product of J and X, but it's not the whole product. It's the product that it's the product subject to a constraint. What's the constraint? That if I take something up here and look at its image under U, it's the same as the image of something here under F, same as the image of something in J under F. Okay, so that's you can take that as a definition if you like, or you can see it as a characterization if you know about pullbacks. Okay, so like I said, I've got this new family, and we can just do a little calculation. I've already told you the answer, but we could say, well, what are the things that U prime maps down to J? Well, that's just my U prime inverse of J, and that means I look at, and U prime is a projection, so U prime just projects down onto the first component. So if I fix that first component, what I've got is the set of x's, right? I'm fixing J. I've got the set of x's that have the same property, but now my J is fixed. So that's all the x's that F maps to J. So that's just U inverse of F of J, and that's exactly what I've written here. So I've got this, if I substitute, I get a new family that has the property that the things that it maps to J are the things that the old map used to map to F of J. Okay. So sometimes you write F star of U for this map U prime. I don't know how consistent I'll be about that. All right, so let's have some examples. So in the first case, I want to look at what happens when X is a one-element set. Okay, so this is a simple case, so let's have a look. Then what F is doing is just picking out an element of I, right? It's picking out an index. Okay. So if I calculate, well, I want to calculate Y sub J for every J that I have, but I've only, sorry, yeah, thank you, I drew this in the wrong place. What I want to do is calculate F sub J for every little J in J, but I've only got the one. So I'm going to calculate. I'm going to calculate what it is. So Y sub star, that's U prime inverse of star. What is that? That's all the things in X, so that U of X is, well, whatever F of star was, but F of star is just I. And of course, this is just exactly the set we're calling X sub I. Okay? So what we've said is that if I look at y, that's the union of all the j's down here, the yj's for all the j's down here. I've only got the one. So y is the union of all the yj's. Well, there's only the one. It's y star. So y star and y star we've just calculated is x sub I. So what we've said is that if you substitute along a particular element of I, then you're just selecting the fiber that corresponds to that element. Okay, so that was a little easy case. Yeah?
Sorry, what is the little square in the upper left side?
This, what does the square mean, this one? It means that it's a pullback.
Oh, right.
Okay. Yeah, it's just a diagrammatic notation. Okay. Okay. All right, so let's have another example. So let's erase the singleton set here because I don't need to have that anymore. So now I want to look at something where I is the singleton set. So this is sort of a non-index set, right, because everything has the same index. Okay, so play the same game. For every j and j, let's calculate the fiber, whoops, shouldn't say that, the balloon over little j for a little j down here. How do I do that? Well, I know that that's the set of pairs, the set of elements of x, so that u of x goes to, well, whatever f of j was. But f of any j is just star, because it's the only thing it can go to. Okay? And this is what we were calling x star. But x star has to be all of x, because there's, u is supposed to map x down to star. So everything's, somehow u maps everything to star. Okay? So if I look and see what y is again, remember it's the union of all these yj's. Well, every single yj is x, so I've really got j copies, or cardinality of j copies of x. Because remember these yj's, well, we can think of them as being disjoint. Oops, think of them as being disjoint. So that's another simple example. They're sort of dual to one another, right? So one is I do the simple thing. I take the one element set here, and the other one that we just had is I take the one element set here. Yeah.
So kind of like before, where we define exponential objects in such a way to say, oh, now our concepts are actually in the category of objects. It seems like if you have pullback and a terminal object, then fiber gets to be like y in that case is like an internal fiber.
Well, it's like you've got yeah, let's see. I don't want to say. I don't want to say. I shouldn't have said fiber already. Okay, so I don't really want to say that. But I mean, I've just got a. For now, let's just think we've got a universal construction. Okay, of pullbacks, and pullbacks are related to having products.
Yeah, well, it seems like we can construct a pre-image of a set, and that's exactly what's going on.
Yeah, well, what's going on is that I'm talking about substitution, and I want to talk about fibrations. And I want to say something about fibrations in terms of substitutions, but I don't want to just jump there. Okay, so it may be, if you just bear with me a little bit. Thanks. Okay, so I'm going to skip ahead through the example we already did. So let's have another example. What if you have a projection? So now I'm thinking of my f here as being something that takes I cross j to I. So that's gone. So I'm thinking of a real projection function now. Okay, I just want to play the same game. I'm going to go a little faster now, though. Oops. Okay, so I've got a projection. I'm going to calculate y. Well, y sub ij, because of course the indices now for y are pairs. So I play the same game. So I've got all the things in x that u maps to, well, whatever f of this pair was. But it's a projection, so it maps the pair ij just down to I. And that's what I'm calling xi. Okay? So if I look at y and try to figure out what it is, like what's up in this corner, just like we've done for the other examples, well, y is just the union of all the y sub ij's now. And every one of those y sub ij's is just the corresponding xi. So what I've actually got, since the j isn't playing any role, I've actually got j copies of xi. So I've kind of got this dummy index that isn't playing any role, right? So that sounds like something that we know from logic. That sounds like weakening. So that's what we're doing here, is if you substitute along a projection, that model's weakening. Okay, I've got one more example for you. So let's substitute along a diagonal map. So now I've got it set up this way. I probably should have called it J, but I didn't. So this is a diagonal map. So if you give me an element, I'm going to duplicate it. Okay. So let's just have one more example for intuition. So what's y sub I? Well, it's all the things in x that u, so that u of x is f of I, but f of I is just the pair I, because after all, that's what f does to an object I here, or an element I here. It just duplicates it. And that's exactly what I was calling x sub I. If I try to figure out what y is, it's just the union of all the yi's, but that's the union over ii of all the xii's. And in other words, what we can say is that y is the restriction of the union of all the xii primes, of the xii primes here, to the diagonal. Okay, so again, I think that's not too surprising once you have a little bit of intuition, and that corresponds to something logically as well. So if you substitute along the diagonal, then you're modeling contraction, right, where you can replace two copies. What are we doing? Replacing two copies of the same thing by just one. Okay, so those are just some examples to try to warm up a little bit, get you used to the idea of thinking about indexing, and allow me to build up eventually to the idea of a vibration. Okay, so the thing is that if I go back and look at my diagram, it's the same one I have on the board here, well, in its pure form, right, way back when, before I started messing with it. So that was J and that was I. So now it's the same map, the same diagram. If I look at the G and the F, we know that those are that G and F comprise a morphism in the arrow category, right? That's how we sort of got here, right? That was the digression that I used to get to talking about morphisms. I reminded you about the arrow category. So I'm going to call this pair GF here a substitution morphism from this thing, which in my diagram here is U prime, but I said we sometimes call that F star U. So I'm going to call GF a substitution morphism from F star U to U. It's just a name. Okay. But if you look at this GF, remembering that we have a pullback here, right? This pullback here. And that pullback has a universal property that if you have another thing that looks like a pullback, like a fake pullback, it factors through that. Okay. That's going to give us a kind of a substitution property as well. That's very similar. So let's have a look and see what it says. So this pair GF, this one right here, is such that if I were to take another substitution morphism, so if I take another object and set arrow, and I look at another substitution morphism, G prime, F prime, so I can draw that over here. So I think that's too small for you to see. Let's try again. I've boxed myself into a corner, quite literally. And I'm short, which isn't helping anything. Okay, so I've chosen another object, and I want to make another substitution morphism. Right? That's what I've got in the picture up there, I hope. Okay. And if my new substitution morphism is such that this F prime factors through F, in other words, I'm just going to move this over because it's kind of in the way. In other words, if it factors through F by, let's say, V, Yes? Good? Okay. Then this is a pullback. So now I've got something that looks very fake pullback-ish, right? Because I've got so this y has these two projection maps, one to x and one to j. But z has a projection map to x, and it has a projection map to j. Did you see that? There's the one to j. I have colors. Here it is. Okay? And here's the other one. So I have to have a map like that, such that, among other things, this diagram commutes. Okay? Okay, so I called that H. So what I said is, I have to have an H. I have to have an H that makes this diagram commute. Yeah?
What does factor out mean? Just having the error? Factors out K to J.
Say that again?
If you said if K factors out J.
Oh, no, I didn't mean to. I don't think I said that, but maybe I did. I said if this F prime factors through F. So in other words, if there's a V that makes this diagram commute,
Great.
okay, then, then I have this kind of fake pullback, and that means I've got to have an H here. Okay, so what about that H? Yes, thank you. Okay, it's because, so this is the real pullback, and it has projection map to x and a projection map to j, so that this diagram commutes.
Right.
Okay.
Why isn't the other thing just another pullback?
Well, so how do you do universal properties, right? You say, I've got a thing that has this property, and if I have another thing that has that property, okay, so my other thing that has that property is what I'm calling the fake pullback. Okay, so if I have another thing that looks like a pullback, then it has to factor. Okay, so that's all I mean. Okay, and so it's got a projection to x, it's got a projection down here to j, and because this diagram commutes, let's see, what has to commute? This diagram commutes, so it really is a fake pullback. Okay, so I've got to have this h here. Okay, yes? Because that's the definition of a pullback. Okay. So the definition of a pullback is that there has to be a unique mediating morphism between the fake thing and the real thing. Okay. So let's just have a look at the properties of this H. So this H, remember the codomain vibration? Yeah, that was a couple slides ago. We didn't really use it, but now we're going to use it. Okay. So remember what it does is it mashes everything down onto the bottom level. So this H, this pair HV is a morphism, and if I look at its image under the codomain vibration, in other words, if I mash it down, I just get V. Okay, that's what I've said right there. So the codomain vibration applied to HV is V. And G composed H has to be G prime. So in other words, here's G prime, and if I do H and then do G, I have to get the same thing I would have gotten if I had followed G prime. That's just, condition for being a pullback. So what we could say is that this GF is the best substitution morphism. So I've said GF is a substitution morphism from F star U to U. But it's the best one in the sense that if I have another one, right, that I said suppose I have another one, it has to factor through my best one. Okay, so this property of having best substitution morphisms is what makes this codomain functor a vibration. Does that make sense? So I'm going to give you the definition of a vibration, but I'm just trying to show you that it's nothing scary. It's just about substitution. Okay, yeah.
So is best substitution, having a best substitution morphism, does that entail something extra to this pullback condition? Or?
No, remember I started off saying, okay, I'm going to try and tell you about fibrations, and a fibration is just a functor from some total category to some base category, and we started looking at indexing because it was a nice lead-in, and I said, okay, well, a fibration is not just a functor, because if it were a functor, then it would be silly to also call it a fibration. Okay, so I said there are going to be these extra properties, and the extra properties are going to be good for talking about indexing and substitution. So we know, hopefully I've shown you a little bit about why substitution is linked to indexing. So if I'm saying that this U has to be good for indexing, then I'm kind of saying it has to be good for substitution. And here we're talking about being good for substitution in the sense of having a best substitution morphism. And what I've said is that's really the essence of being a fibration. Okay. So I could have just started with this slide, but I didn't. So I chose to take the long, circuitous, hopefully scenic and beautiful route. Okay. So to tell you what a fibration is, I have to tell you what Cartesian morphisms are. But you already know because they're parts of best substitution morphisms. Okay. So suppose I have this functor U going from E to B. In my examples, E was, so B was a set, an index set. Well, I called it I. And X was a union of a bunch of categories. But now I'm just saying let E be some category and let B be some other category, and suppose I have a functor, okay, because I want to generalize. Okay, a morphism G going from Q to P in E. So I've got, I'm up here in this total category, and I've got a morphism that goes between two objects in the total category. It is said to be Cartesian over a morphism down in the base. So G lives up here, and F lives down here. I'm going to have a picture in just a minute. Said to be Cartesian if, well, first of all, the image of the one up here is the one down here. Okay, and secondly, if every time you're up in the top and you have a factor, you have something else up in the top that has the same codomain, and it factors, and its image factors in some nice way, then you get something up in the top that factors in a similar way and also has the image, its image under U is the factor down below. So here's a picture. It's easier to see in pictures. Okay, so I've got this morphism G going from Q to P. And it's Cartesian over F going from X to Y. If, first of all, the image of G under U, my functor, is F. And secondly, if I take a fake G that goes from a Q prime into the same codomain, and if I look at its image, and every time I look at its image, the image factors through F, then I have to be able to factor the G prime, the fake G. That's what we just had, right? Because what we said is, so what I would say is G is Cartesian over F, because every time I take a fake G and I look at its image, where did its image go? It's here. I look at its image, and it factors. Oh, sorry, here's its image. And it factors through F, then I have to have something else that U maps to that something else. Okay, so that's not U of the something else is the factor, and I also get a commuting diagram. So this is my map of my diagram up in G, up in E. This one is my diagram down in B. And this diagram is just sitting right on top of that diagram. So that's what I've got here. So this triangle is this one. And this triangle is this one. And what we said is whenever this F prime factors through F by V, then I've got something H that lives above it, in this case in the codomain vibration. And my thing that lives above f prime has to factor through the thing that lives above f, and it has to do it uniquely. Okay, so it's exactly what we were just talking about, but in a general setting. Okay, yeah?
So the information there is that the u's and the u prime and the u double prime are like just what the functor is to the top diagram. Like you're going one category to two different ones.
So the u and the u prime?
And your diagram on the board.
Over here, this one here?
Those are just like
So,
what the functor is doing to the top diagram and putting it in the bottom one. But in that case, you're just drawing one category.
yeah. These are in two different categories. This diagram.
I know, that one's two different ones, but that one's in one category.
This one was in one category. That's true, because I was just looking at what was going on in set, trying to build some intuition. Yeah. Okay, was there a question over here as well?
Yeah, the G prime, the domain of G prime, is it Q prime?
It's some Q prime.
So,
Mhm.
yeah, it says Q to P as over.
Okay, thank you.
Okay.
Okay, yes, so there should be a prime right here, right there. If I hold the laser on it, it might sear a prime into the... Okay, yeah, so it's as in the picture. So thank you very much for that. I'll try and repair that in the slides, but again, the ones on the OPLSS website won't be updated because I don't want to burden Jim too much. Yeah, it makes more sense when it's right. Yeah, sorry about that. Okay. Okay, so those were Cartesian morphisms. So they're good for substitution, right? That's what we just said. Op Cartesian morphisms, I could say very quickly, just turn all the arrows around, right? But let's say it a little bit differently. So let's just go through and spell out what that means. So again, suppose you have a functor. Then I'm going to say that a morphism, and I'm going to use the same names. So a morphism G going from P to Q is going to be op Cartesian over another morphism down here, F, if, well, U maps the morphism in the top to the morphism on the bottom. And now I have kind of the opposite picture. So this is the picture we had before. Oh, and I managed to have the Q prime there. But this is the picture we have for op Cartesian. So now the P is in the domain. And I'm saying that G is op Cartesian over F if, first of all, G is over F, so U maps G to F. And secondly, every time I look at another morphism here, a fake G, and its image factors through F, then G must have factored through, then G prime must have factored through G in the same way. So the same thing. So we have Cartesian morphisms and op Cartesian morphisms. Is that okay? Okay, you're almost there. Okay, so let's make some observations. Let's just take a breath and make some observations. So if P is something up in your total category, let's go back here. If P is something up in E in your total category, either the codomain of some Cartesian morphism or the domain of some op Cartesian morphism. So if you fix that P, and then you look at, so I fixed my P up on top, and I'm going to look at an F down below, and depending on whether I want to look at Cartesian morphisms or op Cartesian morphisms, I'm going to let P be the domain, above the domain or above the codomain of F. But then I could say that a Cartesian or op Cartesian morphism over F with respect to P would be unique up to isomorphism. Okay? So it's maybe best just to talk about one of these. So I think I can erase my pullback diagram now. Say that again? No, this is the real board. Ah, okay. Do you want me to repair this? You can repair it mentally? Okay, I'll leave you to the task of repairing mentally. I will. You just did it because you wanted to see me jump, right? Okay. That was pretty dramatic. I was like, ooh. No such luck. Okay. So if I pick this if I pick this P, a really big P up here in E, so we have a really big one, okay, and I pick some morphism down here, and the idea is that U sends P down to Y, okay, so I called that F. Then I claim that the Cartesian morphism over this F, if I also fix P, is unique, and similarly for the op-Cartesian morphisms. Okay, and because of that, I'm going to call the Cartesian morphism. I'm going to denote it like this. That's a section. I don't know how big it is. It's a little section sign. So F section. Okay, so I'm going to just write F section for sub P, if I remember the sub P, for the Cartesian map over F. And I'm going to write F lower section for the op-Cartesian map, so the P will be on the other side. Okay, and because it's not good enough to just have one fancy name, we're also going to have a fancy name for the domain of the Cartesian map. I'm going to write that as F star P. And for the op-Cartesian map over F, when I've fixed P, I'm going to write sigma sub F of P. Okay. Yes?
Does it exist necessarily or not?
Say that again?
Does it exist necessarily? Are you saying that if it exists?
If it exists, I'm going to give it a name. Yeah. Okay. So what I want to, so I'm just saying what it means to be Cartesian and op-Cartesian, yeah. And I'm not saying anything about whether or not they exist for the moment. Okay. Okay. But now I'm going to. Okay, so finally, what's a fibration? Okay, a fibration is, it's a functor. But you already knew that, because I told you that on the first slide. Okay, well, the second slide maybe. Okay, but it's a functor is a fibration if every time you choose a P, right, every time you choose this P, and every time you choose a morphism, there's a Cartesian morphism over this one that has that codomain. And similarly for op-Cartesian maps. So it's really important to get the quantification right. I think it can feel a little bit funny. So, okay, so I start off with P so up here I'm in the total category. This is up in E, and this is down here in B. So I start off with an object in the total category, and I look at a morphism that has codomain Y, where Y is the image of P under my functor U. So I could write it that way. Okay, and what I'm saying is that there has to be, if I have to have a fibration, I have to have all these Cartesian morphisms. Okay, so that addresses your issue about existence. Okay, so what does that mean? Well, it means I've got this morphism here. So given a P and given an F, it means I've got this morphism such that anytime I take another morphism and look at its image under U, and it factors through F, then this one has to factor. There's a lot of quantifiers there, and it's important to get them in the right order, but that's what we're saying. So I've got enough stuff to do substitution. And I'll let you unpack the analogous definition for Cartesian morphisms, okay? Yeah, question?
You mean you say F star P there?
I just mean, by definition, F star P is the domain of the Cartesian morphism. Okay? So I already said that if I fix the P and I look at F, then the Cartesian morphism is unique. So it has to have a unique domain. And I'm just going to call that F star P for good reason that I'm not going to share right now. Okay, so I've just said the same thing here for op fibration. And a bifibration is a functor that's both simultaneously a fibration and an op fibration. Yeah? Say that again? Yes. Okay, the question was if the V exists and the H is unique. So yes, there's a unique H, and the H has to be over V, and it has to make this diagram commute. Exactly. So again, I won't erase your favorite diagram over here, but it's exactly what we had over here when it was still whole. Okay. I don't know what we have now. Partially Cartesian something or other. I don't know. Okay. So we're going to use the language that I've been using, which says that if I have a functor and it's a fibration or an op fibration or a bifibration, then I'll talk about an object being over its image under U, or a morphism being over its image under U. Okay, so it's the same terminology I've been using, but now you have it in writing. And in particular, we're interested in things that might be over the morphisms that might be over the identity. And we just call those vertical. Okay, and the fiber EX over an object X in B, so X is down in B, and I want to talk about the stuff up in E that maps down to B. That's just the subcategory of objects over X and morphisms over the identity. So again, these are my balloons. I don't know where am I allowed to draw the balloons? Can I? I'm not tall enough. I'll draw them over here, and I'll draw them in red. So I'll try this. Okay, so here I am. I'm down in B. Pen's not very good. And I've got all these X's, X1, X2. That's enough. And then here I am. Can I erase the big P maybe? I can restore it. I can do that. Here's E. And I want to look at all the things that my fibration U is going to map down to X. And I just call this E sub X1. And I call this balloon E sub X2, and so on for all the other X's that I'm not drawing. Okay, so it's just my balloons. Okay. I know, it's sad. Okay, so now you know what a fibration is. We should all have a moment and cheer, yeah. Did you think you'd make it? Did you think you'd make it?
No.
Okay, but you didn't, but you did.
Yeah.
Okay.
I think so.
You seem to still be kicking, yeah. Okay, so we have this F star P. I'm so glad you didn't let me erase this. So we have this F star P here. Can you guys see it over there? This F star P, this thing that's the domain of the Cartesian morphism. Well, I had to fix my P and my F, so then I get an F star P. Well, I can think of F star as a function or morphism. I can say, well, for any fixed P, F star P is the domain of the Cartesian morphism of that F with respect to that P. And then if I chose a P prime, I'd get an F star P prime, right? So I mapped an object to some object, and I mapped another object to another object. So I've got this map of objects to objects, so that's sounding like half a functor. You can also map morphisms to morphisms. So this map will extend to map morphisms to morphisms, which I asked you to do in the homework. So F star actually makes a functor. And similarly, for the Cartesian maps, you call the codomain, you write it as F star down below. No, I didn't say that. I think I used this notation. And that also extends to a functor. Okay? And the one for Cartesian maps is called the reindexing functor, and the one for, you can probably tell me what the name of the one for the Cartesian maps is? Op reindexing functor, exactly. Okay. Yeah. So here's the diagram with the reindexing functor. The reindexing functor goes backward. That's kind of interesting. So if F goes from X to Y, then the reindexing functor goes from the fiber over Y, so E sub Y, to the fiber over X, E sub X. So you'll see that in the exercise when you do it, if you do it, when you do it. Here's the indexing functor. And if f goes from x to y, then it goes from e sub x to e sub y. So it goes from the fiber over x to the fiber over y. You'll see that as well. Okay, so that's it for defining fibrations. I just want to take a couple minutes and tell you some ways to get some new fibrations from old ones. I'm only going to tell you two because I only need two, and they're both pretty simple. So do you know the discrete category? If you have a category C, do you know how to make the discrete category on C? Right, you just throw away all the... Say that again?
Create a discrete category over a set, not a category.
But I can do it over an arbitrary category.
Remove all the arrows but identities.
Remove all the arrows but the identities. Okay, same thing you did with sets. Okay, of course, because, you know, everything's just generalizing. Okay. So then, if I have a functor, if I have a functor u, right, u going from e to b, then I can make a discrete functor. I just discretize discretize it in the normal way. It should go from the discrete category e to the discrete category b if u went from e to b, and I don't have to worry very much about the morphisms, right, because it's a functor after all. Okay. And the other one I want to tell you about is if I have a category, C, then you know that C to the n is the n-fold product, right? Ed told you about binary products, but you can easily imagine extending to products of n things, right? So with n projections. Okay. So I can also make a product functor. So if u goes from e to b, then u to the n goes from e to the n to b to the n. And what do? I just do everything component-wise. So u to the n of a bunch of objects is just, well, apply u to each of the objects. And u to the n of a bunch of morphisms, just apply u to each of the morphisms. And if u is a fibration, then the discrete functor that you get from u is also fibration. And similarly, if u is a fibration, then the n-fold product of u is also a fibration. Okay, so I think I asked you to show that in exercises too. So mean. But I've stated it here. So if u is a functor, then the discrete functor from u is called the discrete fibration from u. It gives you a fibration. And if u is a bifibration or even just a normal fibration, then u to the n is as well. Okay, I've got a few minutes. I can tell you about fibered functors because they're going to be important for us. And I can tell you about fibered natural transformations. Now, you're hopefully reasonably comfortable with functors by now, but natural transformations maybe a little bit less so. Okay, but still, I can introduce you to the ideas. So I'm going to assume I have a couple of fibrations, u and u prime. Those are just functors that are good for substitution, good for indexing. A fibered functor, f from u to u prime, is actually two functors, f sub 0 that goes between the base categories and f sub r that goes between the total categories. So I have a little picture like this because I have to make the diagram commute. So here I have fr going between the total categories of the two fibrations. Here's one fibration, here's the other one. And here I have the functor f0 going between the base categories. And I just want this diagram to commute. So if I first do fr and then do u, first do fr and then do u, I should get the same as if I did u prime and then f0. Do u prime and then f0. That's a fibered functor. That's it. Well, it's a functor, and then it also has this property. Okay. And Cartesian morphisms have to be preserved. So what does that mean? So it means if f is Cartesian over g, so f is up here in e prime, and if it's Cartesian over g down in b prime, oops, oh, a little too fast. Then if I look at the image of f under big FR, I get something that's Cartesian over the image of g under big F0. So this pair of maps preserves Cartesian morphisms. If I have a map here that's Cartesian over another one, I get something over here that's over its corresponding thing. Okay. So I want to tell you about those because I'm going to use those to interpret types in System F. Fiber natural transformations I'm going to use to interpret terms in System F. Okay. So what's going on with those? Well, suppose I have a couple of functors that are fibered over two fibrations U prime and U. A fibered this is a case where the diagram I think is more obscuring than helpful, but I'm going to put it up anyway. So a fibered natural transformation eta goes, so a natural transformation always goes between two functors, right? In this case, I want to go between two fibered functors, F prime and F. Okay? And I'm going to have my fibered natural transformation is going to be two natural transformations. Whoops. Very good with this thing. Two natural transformations, one called eta 0, one called eta r. The eta 0 is going to be a natural transformation between the 0 things. So like down here, I'm going to have a natural transformation. And then eta r is going to be between the things up in the total category. So I'm going to have another one up here, and they're going to be linked. They're going to be linked in just the way you think. So they're going to be linked by the fibration. So let's have the picture. I mean, it's a mess, I think. But here's the natural transformation up in the top. So just take that square and kind of go, whoop. So it's here. It's kind of sitting here. And this square do the same thing. So here it was. Now it's like that. So I've got a natural transformation like that and a natural transformation like that, and they're just linked up by U and U prime in exactly the way you expect. So this says U composed with eta r is eta 0 composed U prime. What does that mean? I've only drawn in one of the squares that look like that, but of course I've got this is the one for x. But of course I've got another one here for y, but I didn't draw that one because the diagram just gets too busy. So this says if I first do eta r and then do U, I get the same thing as if I'd started in the same place and do U prime and then do eta 0. Except that you have to pay attention to which component of the natural transformation you look at, right? Because remember, every natural transformation, it's just like a kind of bundled up collection of morphisms, one for every object, right? So up here, if my eta r is over x, then my eta 0 is over the image of x under my fibration. So it's really nice. I've just taken these two squares, the one on the top and the one on the bottom, gone like that, made one natural transformation sit right on top of the other one, and used the conditions on U and eta to insist that they sit right on top of each other. Okay, I'm going to use these to interpret terms, eventually, terms in System F. So types are going to be interpreted as fibered functors, and terms are going to be interpreted as fibered natural transformations. So like what we did last time. Okay, so this is maybe a good place to stop. So here's what's coming up. You already know, but I'll tell you again. We're going to view Reynolds construction through this vibrational lens. So we already saw it last time with sets and relations, but I'm going to show you how to see that as a fibration, what he did as a fibration. And in particular, he gave these two parallel semantics, right? Like he tried to give like a set semantics and a relation semantics, but they're actually going to be linked up by a fibration. Okay. And then we'll generalize his construction in total categories and base categories for fibration. And we'll do it in such a way that we get an identity extension lemma, and we get an abstraction theorem. And if we ignore size issues, then we'll see that Reynolds construction is actually an instance. So that's it, and a couple of references. If you happen to be interested in this categorical logic and type theory, Bart Jacobs has this amazing book. It's like that thick. It's like this big yellow book. And everything you could ever want to know is in there. It's a really great resource. So, and electronic copies of that do exist as well. So this is a really great reference, categorical logic and type theory. And then this is, again, just a reference to the paper that is linked. Okay, so that's what I have to say for you to you today. Questions about anything having to do with this? No, everybody's stunned into silence. Okay.